In this lesson I will explain what are alkenes, their properties, their nomenclature, their stability and their addition reaction. Okay, starting with few example of alkenes, how we can identify alkenes. Basically alkenes are unsaturated hydrocarbons. So why are they called unsaturated hydrocarbons? Because they have pi bonds. Now you can see there are a few examples. This double line, double covalent bond representing one bond is sigma bond and another is pi bond. So you can see this one is also a carbon-carbon double bond, that one is also a carbon-carbon double bond. So these are the few examples of alkenes. Now let's talk about the nomenclature. So how we give the name of these alkenes. Now you can see in front of you there is the first example. In the first example you can see there are 4 carbons. According to 4 carbon, so name should be but, and there is one double bond. So according to this double bond, so we will add a prefix "ene", so it will become butene. But right now this double bond is in between carbon 1 and 2, so with respect to this we can say it is 1-butene. Okay, if you understand that, so just follow this thing and just look at this example. In this example same number of carbon are there. What is the difference? Only the double bond position has changed. So now you can see now double bond is in between 2 and 3, so name changed to 1-butane. Previously it was 1-butane, now it becomes 2-butene. Okay, now remember that you can also write this name, the IUPAC name, in this way: but-2-ene. Here but is representing 4 carbon, 2 is representing the position of the double bond, and ene is the prefix used for alkenes. Okay, now let's talk about another example. This is the third example. In the third example you can see how many carbon are there. There are 5 carbon. You can also see there is double bond between carbon 1 and 2, so it is 1-pentene. Similar to this, just what is the difference of this in this example? In this example you can see the same number of carbon, there is one double bond, but double bond is in between 2 and 3, so name will be 2-butene. Now this is a very simple example of nomenclature. Now let's talk about another type of alkene. Now you can see it is a cyclic compound, and in this cyclic compound we have only one double bond. Now you can see this is the next example, example number 5. In this example now you can see there are 6 carbon. Yes, now and I have starting the numbering from the right hand side instead of the left hand side. So why I have started numbering from the right hand side? Because when I start numbering from right hand side, so I get carbon double bond on carbon number 2. But let's suppose if I start numbering from the left hand side, 1, 2, 3, 4, then I will get the carbon double bond on carbon number 4. That is not correct. So remember that we will always write down the numbers of the carbon where the group, right now our group is alkene, should be near. Okay, so according to this, let me erase first. Yes, according to this, what is the name? Name is 2-hexene, because there are 6 carbon and double bond is on a second position. Okay, now this is also very good example. Now you can see 6 carbon are there, but right now the double bond is in the middle. Basically it is between 3 and 4. Okay, so if I start numbering from the left hand side, I will get on the third number carbon, as well as if I start numbering from the right hand side, I will also get the double bond on the 3 number carbon. But right now we have one thing more, that is a substituent. So why I will start numbering from the left hand side? The reason is that the substituent is near. Remember that if the functional group such as alkenes in the middle, then we will prefer the substituent. Okay, according to the substituent it is methyl. Remember that, if you just remember the name of this substituent is methyl. Okay, remember that we also call this substituent as branch. So this is methyl, and methyl is attached to the carbon number 2. So first I will write the name and the position of the substituent, that is 2-methyl, and continue with that. As the double bond on third number carbon, so it is 3-hexene. So the complete name will be 2-methyl-3-hexene. Okay, good. Now moving forward, another example here. This is also very important example. Okay, right now we are taking the longest carbon chain is like this, and we are making this one as a substituent. Okay, remember that. Now if I start counting the number of carbon, 1, 2, 3, 4, 5, so I am getting 5 carbon in longest carbon chain. Okay, if you just remember recall your alkane nomenclature, so in alkane you just studied that we should take the longest carbon chain in which we have maximum number of carbon. So if I follow that instructions, so what I will get, let me change that thing. Let's suppose I am starting to take this carbon number as carbon number 1, 2, 3, 4, 5, 6. So this will be the carbon chain. So can I take this longest carbon? The answer is no. Why? Because I am not taking the carbon-carbon double bond in the chain. So that is the reason I cannot take this as longest carbon chain. So I will take the last. I have already mentioned the number. Now you can see this is carbon number 1, this is carbon number 2, 3, 4 and 5, and this will be the substituent. According to this, the name should be, okay, remember these are 2 carbons, so the name will be ethyl. The name of this substituent is ethyl. So, and it is also on a carbon number 2, so 2 ethyl, and the double bond in on between 1 and 2, so it is 1 pentene. The complete name 2 ethyl 1 pentene. Okay, now we have another example in which we have 2 carbon-carbon double bonds. Okay, the longest carbon chain is just like this. Yes, and this will be the substituent, as the substituent is on the left hand side, near to the left hand side. So the reason is that I have started from the left hand side. First I will write down the name of substituent 2-methyl, and then I will write 1, 3. Remember that I am writing 2 numbers. Why I am writing 2 numbers? Because I am mentioning the position of 2 double bonds. This is double bond and that is also a double bond. On carbon number 1 and carbon number 3 we have double bonds. So that is the reason I have written 1, 3 butadiene. Okay, now let's talk about some examples of cyclic alkenes. Now this is the first example. This is the first example of cyclic alkene. In this example you can see there are 6 corners, so each corner representing a carbon, and we can see, so why we are starting numbering from this carbon, because in this area, in this carbon we have a double bond. So remember that when we have only one double bond in a ring, so we will start numbering from that carbon. So number 1 carbon this, and this is number 2, 3 and so on. Okay, and you can also see there is one substituent, that is methyl. So according to this, how I will name this, 1-methyl because it is on first number carbon, and cyclohexene. This is the second example. In this example you can clearly see there are 2 double bonds. Now I am starting from here. So this is carbon number 1, 2, 3, 4, 5. So you can see on carbon number 1 I have a double bond, and on carbon number 4 I have a double bond. So I will write 1, 4 cyclohexadiene. Why diene? Remember that because there are 2 double bonds. Okay, now this is a cyclic compound having 5 membered ring. Okay, now you can see from where I have started the numbering, where the double bond. Okay, so this is carbon number 1. So according to this, 1, 2, 3, 4, 5. On the carbon number 1 I have a substituent, on a carbon number 5 I have a substituent. So first I will write the name of the substituent, that is 1, 5 dimethyl, and then I will write the name of the cyclic compound, that is cyclopentene. Okay, now I will explain the addition reaction of alkene, and remember that the addition reaction of alkenes are also termed as electrophilic addition reaction. What is the reason why they are called electrophilic addition reaction? The answer will be explained in the mechanism. Let me tell you the mechanism. In the first step of the mechanism, the pi bond, remember that the most reactive part of the alkene are the pi bond. The pi bond directly attack on the electrophile. So that is the main reason we say that the alkene give electrophilic addition reaction. Okay, let me show you how it happens. Okay, this is the very simple example of alkene. Right now this one is alkene, and this one is carbon number, let's suppose this one is carbon number 1, this one is carbon number 2, and carbon number carry 2 hydrogens, but carbon number 2 carry 1 substituent. Let's suppose it has methyl, and the other part also carry hydrogen. Now I just made this thing different, but this is still alkene. Okay, with the help of this pi bond, it will attack on the positive part of the reagent. Remember that the positive part of the reagents are also termed as electrophile. So what will happen when it will attack on a positive part of the reagent? It will make a carbon cation. So positive part of the reagent, that is electrophile, will attach on carbon number 1, but the positive charge, or you can say carbon cation, will be formed on carbon number 2. So what is the reason for that? So this is also a very logical thing to understand. Remember that the positive charge always will be formed on more substituent carbon. A reason for the stability of carbon cation I will also explain in this video, so please watch that video till end, that I will explain why the more substituent carbons are more stable. Okay, moving toward the next step. In the next step, that the nucleophile will attack on the carbon cation, and now here the question will arise, where this nucleophile come. Okay, remember that in the first step, what I just already explained you, that the reagent positive part. So the reagent positive part is always termed as electrophile. Now when the reagent positive part will going to attack in the first step, then what part will left of the reagent? So the nucleophile, that is the negative part. Okay, now the negative part will attack on the carbon cation and it will give us the final product. Okay, now this is the simple mechanism of electrophilic addition reaction. Okay, to have better understanding of the electrophilic addition reaction of alkene, now I will explain the mechanism of addition of HBr. So if you just remember the what will be the first step, in the first step carbon cation will form. So how the carbon cation will form, if you just remember, HBr is an acid, so it will give proton to the alkene. Okay, with the help of this double bond, it will going to attack on the proton. Okay, remember that this part is partial positive, so I can call this one as electrophile. So in the first step you remember that the electrophile going to attach on the alkene. Okay, what we will get in the carbon cation will form that H, that is acting as a electrophile, will going to attach on the one carbon, and the second carbon will be carrying a positive charge. So this is the first step. Okay, what will happen in the next step? In the next step, remember that I already explained you that the nucleophile, the other part, and nucleophile here, the nucleophile is bromide ion. Now the bromide ion attack on the carbon cation, giving us the final product. In this slide, I will discuss what is Markovnikov rule. Number one thing, the statement of the Markovnikov rule, that when HX is added to an asymmetrical alkenes, the negative group of the reagent always attached to the carbon atom which has greater number of alkyl substituent. Okay, remember that the negative group, or you can also say the nucleophile, basically it will always attach to the most substituent alkyl group carbon. Okay, now let's understand this rule with the help of one asymmetrical alkene. Now this one is asymmetrical alkene. Right now this one is carbon number 1 and this one is carbon number 2. Now you can easily differentiate difference between the carbon number 1 and 2. Carbon number 1 is least substituent and carbon number 2 have 2 alkyl substituent. Right now this is the difference. Okay, what will happen when we add HBr? Let's suppose I am adding HBr. So number one thing, if you just remember the mechanism, what kind of intermediate it may form. So let's suppose this, I just made a first intermediate. In this intermediate you can see the carbon cation is formed on the carbon number 2, or it can be possible that carbon cation is formed on carbon number 1. Okay, if there are two possibilities, then our product could be two types. Okay, now you can see this one is the first product. In the first product you can see the Br negative part is attached to the mostly substitute carbon, and in the second possibility you can say that the Br is attached to the least substituent carbon. Now if we just focus on the rule, what the rule tells us? The rule tells us that the negative part will always attach with the carbon which will have more or greater number of alkyl substituents. So according to this, our product number 1 is Markovnikov product, but the second product is not correct. Now this is the rule we have to follow. Okay, to understand why we have only this product, so we must understand the type of carbon cations. So I will explain later. That was the first part of the reagent. Now the second part of the reagent, that is called negative. So now it will going to attach to make a final product. Okay, now I will discuss the stability of carbon cation. There is a very basic trend for the stability of the carbon cation, that if you just focus on that trend, that we have 4 types of carbon cation. Number 1 is methyl carbon cation, number 2 primary carbon cation, secondary carbon cation, and tertiary carbon cation. Okay, we can easily identify in primary there is only one substituent group attached with the carbon cation. In secondary there are 2 carbon substituent or alkyl group are attached to the carbon cation, and in tertiary there are 3. So there is a very easy to identify the type of primary, secondary and tertiary. Okay, now here we have to discuss, here we have to find the logic why that tertiary carbon cations are more or most stable. I must say, it should be said they are most stable. Okay, but when we talk about the methyl carbon cation, it is least stable. Okay, now we have to find the reason for that. Okay, first I will take the example of methyl carbon cation. Now this is the structure of methyl carbon cation. If we focus on the carbon of that, so the carbon of this methyl carbon cation is sp2 hybridized. So the positive charge will be spread in the unhybridized p orbital. So this positive charge will be only localized in that area, and it will not find any negative or electron to neutralize this thing. So I can say this positive charge is localized here only. Okay, now let's focus on the primary carbon cation shape. So what we will find, now this is the shape of primary carbon cation, and this area is positively charged. As we already discussed, this thing is carbon cation. Okay, now in contact with, we have a carbon, and this carbon, remember that this carbon is sp3 hybridized. So it will have 4 hybrid orbital, and every orbital will have electron pair. Now any one of orbital may be parallel to this orbital. So what will happen when they will be parallel to each other? So as you know that there is attraction between electron pair and the positive charge, and even the electron pair also repel each other. So what will happen, maybe because of the attraction they will distribute. So they will distribute. What will happen, the positive charge will be delocalized in between these two orbitals. If you just compare this one with methyl carbon cation, you can see in methyl carbon cation the positive charge was localized, but because of this parallel electron pair orbital, so maybe the positive charge will be delocalized. So remember that whenever the positive charge will be delocalized, so it will be less available. If it will be the less available, so it will not react easily. So that thing make him more stable. Okay, similarly when we talk about the secondary carbon cation, so in secondary carbon cation we have two carbons, we have two substituents, so we have a double kind of support here. And when we talk about the tertiary, in tertiary this support will be 3 times. Basically we call this thing as a hyperconjugation. Because of this hyperconjugation, what happens, the positive charge on carbon cation is delocalized, and when it is delocalized, it make carbon cation the most stable one. When it will be more stable, so it will exist more. So that is the reason we can say here that the methyl carbon cations are least stable and the tertiary carbon cation are the most stable. Thank you.